Awesome, thank you. Check, check. Sounds good. Thanks for the introduction. Again, yeah, Declan Magis. So yeah, in particular, in the navigation world, I'll be talking more specifically about optical navigation, but also trying to give a whole background on what interplanetary navigation is. There's a lot of overlap with astronomy, especially in the optical navigation side. I think, healthy balance of high level with a little bit of getting into some technical stuff. I am very prone to spitting out acronyms that no one in this room will have heard, so please feel free to ask questions and call me out whenever I'm spewing a bunch of acronyms and haven't explained what they are. All right, so to just reiterate about me, I grew up in the Bay Area. I grew up in Oakland, graduated from Cal Poly in San Luis Obispo with a master's degree in 2019, so just moving south through California basically. Yeah, it was really my senior project where I first kind of got my introduction into deep space navigation, and in particular asteroid deflection, which happened to be very applicable to my immediate role when starting at JPL. I basically really got into the field when I took fall of 2018 off for an internship at JPL, where I got to work on the navigation team, working the New Horizons flyby of the Kuiper Belt object Arakoth, or 2014 MU69. And then shortly after that, I started at JPL, January 2020 in the Outer Planet Navigation Group in the Mission Design and Navigation section. Here's a graphic of that's the Kuiper Belt object Arakoth that was flown by on New Year's Eve of 2018, or 12:30 in the morning, January 1st, 2019. It was kind of a fun New Year's Eve party while anticipating the flyby. It was great. And then that's a just fun graphic of my asteroid deflection senior design project. A little bit more, so more into the time at JPL. So I worked on the Hayabusa 2 sample return. That's a JAXA mission. The DART mission, Double Asteroid Redirection Test, that was managed by APL, a NASA mission, and LISHA-CUBE, which is an Italian space agency mission that was flying along with DART and captured images after the impact. And I'll really go into depth on that mission later on. Otherwise, I've been doing some research on interstellar object mission analysis, kind of a pet project of mine. I've been working on Mars sample return for a while. Various outer planet concepts, doing analysis for future missions, Enceladus plume sampler, doing a decent bit of work these days on autonomous navigation, kind of a rich field that's being explored these days. Uranus mission, outer planet stuff. Currently working on the Martian Moons Explorer mission, another JAXA mission called MMX, and that is a sample return mission to Phobos. So really looking forward to that. That will be launching next year. And then also doing some research in ion beam, asteroid diffraction, really just a kind of big variety you get to work on while doing navigation. You kind of get to have your hands and feet in a wide variety of missions and be involved at all stages. So about deep space navigation. Nice overview of what it really means to be a navigator and to navigate a deep space spacecraft. So there's really 5 steps here, kind of trying to show the example in space and what the example really is on the ground. So task 1 is obtain a map. So on Earth, you need your road map, you need to, you want to have your elevation and understanding of the terrain, have this database, and you're using that to kind of look at and plan and be able to know what it is you're going into. And in space, that is the planetary ephemeris. That is creating your models of the solar system that describe all the dynamics. Where are the planets? Where are the asteroids? How do they influence orbits? All of that. That's building up your map. Then 2, you have to develop a travel plan. So on Earth, you're selecting trails to reach a certain destination. Where do you want to go? How do you want to get there? In space, that's really the trajectory design. That's selecting your orbits, given your knowledge of the planets and where they are and all of their trajectories. What is your path? What maneuvers are you getting? What turns are you going to take to change your trajectory to get to where you want to go and at the right time? Now, given you've embarked on this plan, as you are on this journey, there's step 3, which is take meaningful measurements. So on Earth, you're kind of, you're noting your time as you pass through landmarks. Oh, when did I climb over this pass? And and is that on schedule? What direction am I going? If now you have lots of digital maps, but if you have a compass, you're looking at where you're going over time, trying to collect these measurements to understand how well you're executing that plan. And in space, you're collecting radio signals and optical measurements. You're basically, I'll go into this more. You're getting tracking data and collecting these measurements that measure information about the spacecraft and its trajectory. And then with all those measurements, you're going to try and calculate your position. You've collected these measurements on Earth, but what does that actually mean? Like, where are you actually, and where do you tie that in? And you have to tie that into your 2-year map, tie that into your plan, and understand where you are, and use those measurements to make a meaningful statement about your current journey. In space, that's really, you're collecting all these measurements, and what is the trajectory I'm on? What am I doing? Where am I? Where am I going? What is my velocity, position, relative to all important bodies, all of that. And now that you know that, you can then determine, am I following this plan as desired? Is there a new, more optimal route to do? Should I, when I'm on Earth, do I have to start speeding up if I'm going to make it to camp before sunset? Or, do I have a lot of time? Maybe I could slow down and be more efficient. Versus in space, we execute maneuvers. We have to tweak the trajectory and impart forces on the spacecraft to alter its orbit. And that's really the fundamental role of navigation, is completing all these steps. So to connect things to kind of how stuff is done near Earth, we're talking deep space, but near Earth navigation really just have access to this beautiful thing called the GPS system, which is kind of graphically represented here. We basically have a constellation of GPS satellites, and they transmit time-tagged signals with information on their position. So your cell phone, your devices are able to collect these signals, and it's basically a form of triangulation of like, oh, I received this time-tagged signal from a GPS satellite in this position, and it has this time, and it was sent at this time, and I received it at this time. So you kind of can know how far away you are, and then you're supposed to know where it is. That's encoded in the message. And then if you get those signals from multiple spacecraft, you're able to just directly triangulate your position. And that's just extremely powerful. You can just constantly be collecting these signals, getting really precise, 3D position measurements constantly. So GPS is just extremely powerful, and we on Earth use it, and so do spacecraft. And it just, for all spacecraft in orbit, they're really able to leverage this. There's also lots of ground observations that spacecraft, especially non-cooperative ones, there's lots of imaging that's done to kind of update orbits and all of that. But when we're in deep space, there is no GPS. There really is a finite range in which you can collect these measurements. You can kind of collect weak GPS measurements near the moon, and there's a lot of research going into that. I can't comment too technically on, not something I've exactly looked at, but yeah, once you really get outside the moon, you're not getting GPS signals. So what do? We have the Deep Space Network. So this is a collection of 3 major stations, 3 locations spread out, as you can see on this kind of top-down view in the bottom right, really spread out, exactly into thirds around the globe, spread out evenly such that when you look at their field of view of like what range of sky, what area of sky they can see at any given time, you basically get full 360-degree coverage of the entire ecliptic, basically. Directly above and below, often interplanetary spacecraft aren't going to be there, so it's not like we need a station on the poles. But yeah, so basically these are bases full of just massive communication arrays, 50 meters, lots of 30-meter dishes, with the largest going up to 70 meters. Yeah, and there's one in California, Goldstone. I think there are tours, and I would highly recommend people look at going to check that out. It's really an incredible facility. Yeah, then there's one in Madrid, Spain, and Canberra, Australia. And so basically these are the tools that we use to communicate with essentially all interplanetary spacecraft. There are other agencies that have been building up their capabilities, but it really is the Deep Space Network that's been enabling interplanetary missions. Oh yeah, first became, originally built in 1958, established, and officially became the DSN in 1963. And these facilities are run and managed by JPL. So what are the measurements that the DSN provides? So the real bread and butter of navigation is Doppler data. So basically these stations, the spacecraft, are communicating with them, sending signals at certain frequencies, and basically we are tracking the shift in frequency due to the relative motion. So, the phenomenon that we all can experience and experience here on Earth is it's kind of the situation where you have a car driving at you, and if you can imagine that car honking its horn at you as it's driving by, and the change in the sound of that horn as it goes, but it's the same sound coming out of the car, but because of that car's motion coming towards you, it's compressing those frequency waves, and then when it's driving away from you, it's stretching them out. And so we basically are observing that exact same phenomenon, but with different frequencies, not in the sound frequencies, but in gigahertz, X-band, various communications frequencies. And what we basically measure is the relative motion between the spacecraft and the Earth along the line of sight of the station. So you can only measure how fast the spacecraft is moving away from you or towards you. You cannot measure how fast it's going in orthogonal perpendicular directions. You can't measure how fast it's going side to side. You only get to measure how fast it's moving away or towards you. But basically, if you collect enough of those measurements, and you collect those measurements over a long enough period of time, they really can directly inform on what the exact trajectory is of the spacecraft. All the dynamics of orbits and gravity are very well known. So if you collect these measurements and know its velocity at all these times, you can piece together and determine the trajectory. And I'll talk about that a little bit more. To go along with that, there's also range data. Similar to the DSN, you're basically sending a time tag signal, and you send this signal here, and how long does it take to get to your spacecraft and get back to you? That can inform how far away you are. And then there's other measurements, more complicated measurements and powerful ones like a delta differential one-way range. That's kind of a more complicated measurement that involves multiple stations and can basically, somewhat similarly to range, you can kind of think of it as, in a way you're getting multiple angular measurements from multiple locations, so you can really kind of triangulate the location of your spacecraft, even at great distances. It's a very powerful measurement and enables a lot of direct triangulation of where a spacecraft is in the plane of sky. Because again, Doppler data, you don't see how fast it's moving side to side, so to a certain extent, you don't have that much observability into that. Delta Dor is a measurement that comes in and kind of gives you that direct observability of where something is moving in the plane of sky. The graph up on the right kind of really depicts what Doppler data looks like. So basically, you have that dotted line, which is the spacecraft's long-term orbital velocity. It's slowly, just say it's slowly moving away from the Earth over multiple days or weeks. But at the same time, the Earth is also spinning. So you have a station on the Earth. So as that station spins and spins away and then spins towards, you get this oscillating signature from the change in velocity. It's spinning away, so it's slowing down, and then the station is no longer in view of your spacecraft because it's on the wrong side of the Earth, and then it comes back into view, and then it's spinning away, and then it goes back out of view, and so you get these kind of interesting signatures, and depending on whether the spacecraft is directly above or where it is kind of on its latitude, you get different signatures in this kind of short-term oscillating period. And so you're able to get kind of interesting additional observability instead of just this long-term term, because we have our stations on a rotating surface unit. So now we can kind of get into this third data type, which is really my specialty, which is optical navigation. So with DSN radiometric tracking data, we're really able to observe where these spacecraft are just directly relative to the Earth. We're getting all these measurements. The stations are on the Earth. We're measuring what they're doing relative to those stations. But we're sending these things out into the solar system, multiple, millions of kilometers away. Often the unit is AU. If anyone is familiar with this term, it's astronomical unit. It's a common metric. It's the distance between the Earth and the Sun, and so it is used to describe how far away things are. 2 AU, 3 AU, 4 AU. So we're often collecting, sending these spacecraft to things that are 10 AU away from the Sun. Really, these massive distances, and at those distances, we can't just send the spacecraft to a location in space. The asteroids and outer planets in the solar system are not known exactly perfectly. We collect lots of astrometry data, we fit their orbits, but again, these things are so far away that even with the highest resolution imager, you still have kind of finite measurement accuracy at these distances. And so that often maps into tens to hundreds of kilometers of kind of uncertainty where these objects are, just due to the distances. And so you can't really just send, if you don't know where something is to 100 kilometers, it can be very challenging to just send a spacecraft there and say, yeah, go to this area around, a couple hundred kilometers and, maybe we'll get into orbit, basically. That's often not going to fly. Some objects we do know really precisely, especially the ones we've been to a lot. We really know where they are, and you can just send a spacecraft there, know exactly where the spacecraft is, and you know where the target is well enough that you just track where the spacecraft is and can control it and maintain it and get it into an orbit around a body or execute a flyby. But for these other objects that are particularly uncertain, we leverage optical navigation. And this is where there's a lot of overlap with astronomy, because optical navigation is kind of just, in a way, space-based astronomy. We basically have an imager on a spacecraft that takes pictures of its target on approach. So the spacecraft basically has its own pair of eyes. As it goes towards these, let's take an asteroid, for example. Initially, it's just as far away as the Earth is, so it's not really going to be improving our knowledge of where the asteroid is, but it's going towards that area. So eventually, it's going to be 10 times, 100 times closer to the asteroid than the Earth is. And so at that point, your resolution of your imager is really producing a really accurate measurement just due to how close you are. And so by taking images on approach, we're able to refine and collapse these uncertainties that would otherwise make it impossible to go visit these bodies. And that's optical navigation. Kind of going into the steps, and I'll go into the implementation of these steps, in particular for the DART mission, kind of walk through how this goes. Again, it's very similar. You're developing a plan. When are we going to take images? When is it going to be bright enough for us to see? When are we going to be able to downlink these images? You're developing this whole plan to synergize with the DSN data as well, and plan out your imaging. Then you launch, and then a key step is calibrating the cameras. Maybe a process many of you have gone through as well in ground-based astronomy. But yeah, basically, especially due to launch, you're basically sending this very precise imager through a pretty intense launch environment. It's also been sitting on Earth in a nice, benign environment, and now it's in the intense thermal environment of space, getting direct sun or extreme cold, and so you get lots of distortions. The spacecraft, the camera you've built, and the telescope and optics you've assembled on Earth are not going to be exactly what comes out at the end of an intense launch vibration environment and these new thermal environments. So you always need to calibrate your camera. I mean, these are very well designed instruments, and so it's usually very tiny changes, but it's a very key step. And then we can collect and process our data with our calibrated camera. We can begin taking images. There's really kind of two main data types, which is unresolved targets, where you're imaging an asteroid and it's just a point source. It looks just like a star. And then once you get closer, you might have resolved targets. We have these extended bodies where there's a big distinction between a star point source object and a fully resolved 100 multi-hundred, filling the entire field of view image of a surface in a small body or large body.
Question.
Yeah.
You talked about the deep space network taking measurements from Earth.
Yeah.
You're talking about optical navigation as we're getting closer to target.
Yeah.
But how is the spacecraft staying on track to the trajectory that you've programmed for it to go through to get to target?
So
Once it goes far enough that it's, the deep space network may not be able to triangulate, how does it know that I'm staying on target or on trajectory?
So it'll always pretty much be able to communicate and get data with the Deep Space Network. We still communicate with the Voyager missions. We're not necessarily really trying to get tracking data at this point, but for New Horizons, Kuiper Belt Object, we were at 42 AU was my first experience working navigation, and we are at 42 AU. It was a 12-hour round trip light time. And even at those ranges, we're able to communicate with the DSN. The spacecraft is then itself designed with a very large dish to close that link. But you're still always able to get the data and able to know where your spacecraft is to within, a handful of kilometers, tens of kilometers, worst case scenarios. Often the estimation is even better than that. So you really do always get to know where your spacecraft is, just in the solar system. And so the key thing is just then making sure you know exactly where your target is that you're going to. Yeah. We've talked about all these measurements. Then there's a key final step, which is to do orbit determination. So at JPL, we put all these measurements together into orbit determination filter using JPL's software Monty, which is kind of the gold standard navigation software that has flown the vast majority of interplanetary missions. And basically, what Monty really does is is a toolkit that maintains all the models of the solar system. Anything you care about in the solar system, we can plug in those models and understand how they would affect a spacecraft or affect the measurements. You model all of these things, and you basically put them together with your data and attempt to estimate the spacecraft's trajectory. So this really simplified version of this is what you could do in Excel. You could load up a bunch of data, select that data, and tell Excel to fit to perform a least squares fit and fit a line to that data to minimize the difference between what the line predicts and what all the measurements observe. And to a certain extent, that's what we're doing. We have, instead of just two axes, we have many axes for all these different parameters, but you're basically collecting this data and in a simplified way, performing a least squares fit to just fit this trajectory to all this data and all these models and the parameters. And that's really, really kind of to a certain extent what we're doing. So, getting into a little bit of the details, we're estimating the spacecraft trajectory, which is often just its Cartesian state, x, y, z, vx, vy, vz, at a certain time. And then we're also estimating other parameters. You got to estimate biases in the data. There are other very key fundamental forces that are affecting a trajectory, which is the solar radiation pressure pushing the spacecraft around. How well are your maneuvers being executed? Are there any errors associated with those? There's also, you're getting around all these small bodies. And so we really, need to know these small bodies are imparting forces, gravitational forces on our spacecraft. So we really need to want to know exactly where all the bodies are in the solar system. They have, not everything is just a single point mass gravity. They have extended shapes with, varied gravity fields. So it's very important to estimate how their spin, what is the particular gravity field around that body, how is its shape and density, imparting non-point mass gravitational effects. And then there are other parameters that just kind of affect our measurements, but we don't really need to estimate, kind of like, where are the stations on Earth? We're measuring everything relative to the Deep Space Network to a certain extent. So it does matter where the Deep Space Network then is. We know where these stations are extremely precisely, but it's something you want to consider. Maybe I don't know where that exact location of that antenna is to better than a centimeter or something like that in the solar system. So you need to take into account all of these things. The Earth's orientation, we need to know exactly how the Earth is oriented in order to connect the dots on all these measurements. How is the atmosphere affecting our signal? You know, how is the moon's gravity distorting, it's called earth tide, you know, and how are these tidal effects physically distorting the shape of the Earth by very tiny amounts, but it matters when we're trying to do precise navigation. You know, how is the moon's gravity pulling this one station ever so slightly in a certain direction over time as it orbits? So there's all these things you really need to take into account. And you know, and then we're always monitoring, like, oh, what's happening to the spacecraft that isn't modeled? Why are we seeing this acceleration? What is this unknown acceleration? What are these odd small forces? What is going on? You're really able to just kind of observe, and anything that you're not modeling exactly, you want to figure out, what is it? What kind of model or parameter could we put in here to explain this, basically? And then again, with this trajectory fit, you then can design maneuvers, and you see you're on a certain trajectory. Oh, we need to correct back. So let's design a maneuver and execute a maneuver to bring us back. Just to kind of explain some metrics of how a navigator looks at things. A common term, and I think I'll bring this up later a little bit, is a common metric for navigation performance is the B-plane, which there's kind of a nice graph off to the right that shows how, you know, if for flybys, gravity assists, you really are kind of looking at, you know, where are we going to fly by the body? And that's kind of this, you know, you get to form these ellipses of, you know, let's say this is your target where you want to fly by the body. You know, where are we lying within this? So you typically have like a target, and then you have a requirement, some large ellipse. Like, you have to fly by this body at this exact location to within this range. And so you're constantly tracking, where are we actually flying by it? And also, what is our uncertainty of where we think we might actually be within this nominal center? And so you're always kind of trying to drive your entire uncertainty of where the spacecraft might be to be within your requirement. And then so you fly by it in a certain location, and you want to make sure you fly by it at the right time. And so that's just a common metric that's used to kind of constantly track. A navigator's often really looking at plots like this of, where are we? How are we drifting over time? How is this, you know, this true delivery location moving over time? Are we staying consistent within our ellipse? We're estimating we're going to be here, and to 99% we should fly by here. Okay, we get more data. Oh, we're walking away. Oh, we get more data. Oh, we've walked outside of where we thought we were going to be within 99% confidence. What is happening that we're not modeling correctly? Because clearly something is going on that has driven us outside of what we expected. And so these are really kind of the key metrics that a deep space navigator is looking at. And then otherwise, you know, a key metric is, of course, at the end of the day, how much fuel you're burning. You know, you really want to understand all your uncertainties, and at the end of the day, you want to use as little fuel as possible, fly that, you know, if you could just get on a perfect trajectory and just stay on it and never have to do any corrections, that's the perfect mission, you know, but it never works out that way. I'll go through kind of quickly a kind of a little overview history of deep space navigation now. So really started in 1962 to 67 with the early Mariner missions. 2 through 5, they went and executed flybys of Mars and Venus. Yeah, this is really the, you know, origins of deep space navigation. They performed a single TCM. Basically launch them, then fairly soon after, all right, where do we think we kind of roughly are? All right, just do a burn. Let's just aim for Mars, aim for Venus, basically, and let's just see where we end up, essentially. Trajectory correction maneuver is the TCM. And so, yeah, you're just performing a single one. So they're really targeting really wide ranges, you know, 15,000 kilometers, 3,000 kilometers, because, you know, your uncertainty just propagates over time and it just grows. So you're not really doing close flybys. Then they started to leverage optical navigation, because at this time we didn't really know where Mars was that well. We hadn't been there, so we didn't actually know too precisely where it was. So it was a reasonable time to leverage optical navigation. More expansion, we get range measurements. Mariner 9 was the very first orbital mission. You know, it would perform remarkably. You know, able to predict the spacecraft location 9 orbits out to within 4 kilometers. So you're pretty rapidly starting to improve these capabilities. Mariner 10 was the first gravity assist. and also was, at this time, it was regular to do multiple trajectory correction maneuvers throughout a mission to maintain an orbit. And at this point, we're targeting really close flybys. I mean, you're talking 10 years ago, let's just try and go there within 15,000 kilometers. Now, let's target a 17-kilometer flyby. Or a 17 kilometer, we were delivering the spacecraft to within 17 kilometers of the target. So you're able to control things much more precisely towards this point. Then you get the Pioneer missions, 10 and 11, first missions to the outer planet solar system, performing flybys of Jupiter and Saturn, just important missions to put in the timeline here. Then we have Voyager 1 and 2, the very ambitious missions, the all-time kind of famous interplanetary missions. They tested new technologies, new frequencies, how do we improve our measurements. They were the first missions to require optical navigation, because especially as you're going to the outer planets, they are farther away. Our ground-based observations are less accurate. Therefore, you need to put a camera on to a certain extent, especially when you hadn't been there before and haven't gotten really close measurements. So you require optical navigation due to these just large uncertainties. This mission going way out to Uranus and Neptune. We need to build 70-meter dishes. We need bigger dishes. We're going so far away to have signal that's strong enough. Really incredible, interplanetary mission to Halley's Armada. This was, 5 missions sent to fly by Halley's Comet. Basically, each one walking in closer and closer. Each one providing an update, a knowledge of Halley's Comet, so the next one could go closer and closer. And also, notably, to date, the fastest flybys ever performed at 68 kilometers per second. Then, Magellan to Venus, first test of using aerobraking, really quite a navigation challenge, because now, we're used to flying our spacecraft by saying, do this exact, perform this exact delta V and change your velocity exactly by this. And now you're in a regime where you're saying, all right, let's fly through the atmosphere and attempt to model the atmosphere and understand exactly what is the force that it's going to provide. It's just a very unwieldy thruster to a certain extent. So navigation becomes very important. You have to really track, when you come out of the atmosphere, where are we? What orbit are we on? Did we slow down too much? Did we not slow down enough? There's lots of navigation challenges associated with that. Galileo, first mission to fly by an asteroid and orbit an outer planet. Notably, its high gain antenna failed to deploy, which is pretty important at these large distances. So, it led to lots of new techniques in order to leverage and extract as much information out of the more limited data as possible. Near Shoemaker, 1996, first mission to orbit and land on an asteroid. This is where we're getting into more advanced methods of optical navigation, crater and landmark-based optical navigation. Lots of time we're just kind of looking at it and at a extended body and saying, oh, here's the limb. Okay, well, here's where the dead center of it is. But as you start to really try and do more ambitious missions, you have to have more accurate methods of measuring where you are relative to the asteroid, especially as you orbit it. And so then there's a Cassini launched to orbit Saturn. This is just a notable mission because you get into these flagship multi-billion-dollar missions, and they're often referred to. I didn't get to work on Cassini, but I've always heard it referred to as a Rolls-Royce level spacecraft, where it was just super clean to fly, performed excellently, was just a very clean and navigable spacecraft. Then Deep Space One, notably first mission to demonstrate autonomous optical navigation, also including ion engines, and autonomously performed flybys of a comet and an asteroid. It was 1998 where autonomy really starts to get its first legs. Now, really importantly, also in 1998 was the Mars Climate Orbiter. This is something maybe everyone's heard about. It's pretty famous in a infamous, really, instance of a navigation mishap. Truly. So this was a mission to go into orbit around Mars and measure its climate and perform science. However, en route to Mars, basically, there's a navigation team. They were expecting thrust force files that were supposed to be in Newton seconds. This is the kind of famous units You're going through high school. Remember to check your units, kids, because otherwise you might crash into Mars. Basically, that's this story. So yeah, the navigation team was expecting thrust force files in Newton seconds, but they were being provided in pound seconds, resulting in basically a large error. Forget the exact factor difference off the top of my head. But so basically, the navigation team is, you're estimating your trajectory, and you're also inputting information of what kind of forces are going on. Some little thrusters are firing, and the spacecraft has knowledge of that. It knows how long a thruster fired, and it has an accelerometer, so it can measure these forces. So they get sent to the navigation team, and the navigation team plugs them in. It helps understand the trajectory. And in this instance, they're plugging in just, by a large factor, wrong numbers. And so this issue was not properly diagnosed, and the Mars Climate Orbiter passed by Mars at an altitude of only 57 kilometers, too low, and thus resulting in unsurvivable atmospheric forces. So this really was a very huge event in the space of navigation. It led to a lot of changes. Led to the establishment of the Navigation Advisory Group at JPL, wherein basically top navigators review all major events for every mission. Much more significant reviews. And also it led to the widespread use of Delta Door. So Delta Door, as I mentioned earlier, is this powerful measurement that can kind of triangulate where a spacecraft is in the plane of sky. And if Delta Door had been getting used more regularly on Mars Climate Orbiter, you would have been able to observe the issues with this data. Basically, again, you're getting this Doppler data, but it's somewhat limited. It's only along the line of sight and how fast it's moving away or towards you. And so a lot of these forces were actually being applied in the side-to-side direction. And so they weren't observable. So you were plugging these forces in, and to a certain extent, you have to rely on the fact that they're true. And because you just don't have observability into what's really going on. Leveraging more Delta Door would have enabled the navigation team to observe that something that was actually happening was not what the models were predicting, basically. And you would have been more there's a solid chance this issue would have been caught. But yeah, very famous mishap. Stardust mission, soon after, flyby multiple comets. Again, more implementation of autonomous navigation. Then there's the Hayabusa mission, JAXA Hayabusa mission to collect samples. This is deep impact, pushing autonomous navigation even further to do autonomous impacting. That's this autonomous impactor right here. New Horizons, this is the mission I got to work on. First flew by in Pluto, and then the Kuiper Belt object Arrokoth, most distant flyby ever. Dawn mission really developed optical navigation further. It really leveraged ion propulsion to its fullest. It went and orbited 2 different bodies. It went into orbit around one asteroid, left, and went to another and got into orbit around that one. And we really more advanced optical navigation techniques I'll touch on later, called SPC, stereo photoclinometry. Some CubeSat missions. Really, CubeSats are great. They're really cheap, but they're really cheap, and therefore things go wrong, and therefore they're a lot harder to fly. So it is a known kind of navigation challenge of how do we do cheaper missions that are harder to fly and harder to navigate and still keep them cheap, basically. And then DART, latest implementation of autonomous optical navigation. So more into autonomous navigation. So this is as applied to the DART mission. This is what I really started working on full time when I first came to JPL. It stands for, again, double asteroid redirection test. It was targeting this double asteroid system, Didymos and Dimorphos, with the plan to impact the smaller moon Dimorphos. And then, this CubeSat LishaCube gets deployed and gets to watch the flyby. So yeah, this is an APL mission, but navigation is done by JPL. Again, JPL kind of led almost all the early interplanetary missions. So kind of, again, JPL is the gold standard on interplanetary navigation and mission design. And so we get to work with a lot of other agencies to provide assistance in navigation and shadow navigation, or work with other NASA centers to do navigation and work with their mission design teams. And so I had the pleasure to work with APL both on DART and New Horizons. New Horizons also an APL mission that I got to work on a JPL navigation team for.
I have a question. So it says 610 kilograms wet mass. So what is wet?
That's fully fueled. Yeah, basically fully fueled. So it's a decently heavy spacecraft and trying to impact the smaller moon, because you could change the orbit of the moon relative to Didymos and actually observe that change. If we just hit Didymos, you wouldn't be able to observe the change in its orbit as it went around the solar system. It just is, we would not have been able to impart enough force to really accurately measure what would have happened to the orbit due to the impact. But by impacting the moon, the much smaller moon, in a much smaller orbit, you're able to see a more significant change in the period, and thus characterize how effective the impact was at changing the orbit. And I'll kind of touch a little bit about what one of the really key goals of this mission was to determine how effective kinetic impactors are at deflecting asteroids. So it really comes down to momentum transfer. When you just crash something into something, it imparts the momentum it had into it. Pretty fundamental physics, conservation of momentum math here. But what also happens is you also are creating a massive explosion that's shooting out a lot of ejecta. And you can kind of think of this ejecta as like a little thruster. It's a bunch of materials just getting shot out the back. And so, again, conservation of momentum. If this material is going this way, so this fast, the main body must also have gotten an extra kick going the other way, same proportional to the relative masses. And so, if you impact something, are you going to get a little bit of ejecta, a small momentum increase, or maybe are we going to get a huge blast of material shooting out the back that could provide multiple factors of additional momentum exchange on top of just the raw mass and velocity of the spacecraft itself. And so that was really the key parameter to look at. It's referred to as the beta value of a kinetic impactor, because if you're getting 5 times the momentum transfer, that's 5 times less spacecraft you would have to build to attempt to deflect an asteroid, basically. It's a very important parameter for characterizing a potential real scenario. So onto the optical navigation. So there's the imager Draco, based on New Horizons LORRI, Long Range Reconnaissance Imager. But this is Draco. It had a 4.95 microradian angular pixel size. So that's, I think, just under an arc second. I forget the exact conversion. And yeah, we basically are some limitations. We could only take 90 millisecond exposures. It was a 1024 by 1024 detector. It also was a rolling shutter, which was kind of a new challenge we had to overcome. And yeah, here's the kind of the schedule. So here's kind of a plot of Didymos's apparent magnitude. So we had first detection at around, I think, 15.5 magnitude. This was around 60 days from impact. This is a few hundred meter sized asteroid. And then basically we get early detection, do some early detections. And then once we really start into the final approach campaign, at 30 days out, we were taking 240 images every 5 hours. So just a huge amount of data. The spacecraft was very close to the Earth this whole time. So there was just you had a very powerful communications link that could send vast amount of data. It's really not what usually happens. You're usually much farther away, but we were so close, you're able to communicate just huge amounts of data. And the only thing on the spacecraft really was a camera. There's no other real science instruments. The whole point of it is to just hit this asteroid. So let's take a bunch of pictures, basically. The very last OpNav image was taken at 48 hours from the final impact minus 48 hours. So 2 days before impact was the last OpNav image collected to then inform the design of our final maneuver 1 day, 24 hours. So you collect your last data 1 day before you execute your maneuver. So you have 1 day to kind of process the data and estimate the orbit, design a maneuver, execute the maneuver, and then you execute that maneuver 1 day before impact, and then you basically see how well you did, essentially. But you'd still collect data, so you could see how well you did, but you just weren't doing additional maneuvers afterwards. And this is all ground-based. DART also, as mentioned earlier, utilized autonomous terminal guidance, autonomous optical navigation to do the precise targeting. But up until 4 hours before impact, it was flown from the ground. So, we have this plan. Again, now we have to do calibration. So again, there's all these issues due to launch and thermal environment. So we took a bunch of images of M15, Great Pegasus Cluster. Here you kind of, take a mosaic of all this known star field. You're able to calibrate out the distortions and what happened with the exact optics. And kind of measure the alignment, like how well do we know where the camera is and things are oriented, and how has it been distorted on the spacecraft. And so very, very important step, because that also informs the, that calibration process is then critical for the terminal autonomous guidance. The terminal autonomous guidance needs all this precision updates on the exact alignment of everything in order to perform correctly. So here's kind of the steps. Here's an image. We take this image, we predict where the stars are going to be. We were using the Gaia catalog. You basically predict what stars you expect to be able to observe given your exposure time and where the spacecraft is pointed. But again, the spacecraft is kind of, it has star trackers on it. It has all these other systems that are trying to estimate where it is and where it's oriented. But the imager is really high resolution. It's a really high resolution imager. So these there are other cameras on board that are just constantly imaging the stars, but they're much lower resolution. So they're just not measuring the attitude of the spacecraft extremely precisely. And so when you take this really high resolution image, you get an initial guess as to where exactly that picture was taken, but you only really get to see, you basically use that initial guess to guess where the stars are, and they're close, a couple dozen pixels away. But then, of course, you need to register them and update your knowledge of the attitude of that exact spacecraft, where exactly it was pointed in inertial space. And now, for this mission, again, we could only take 90 millisecond exposures, but we could take a ton of images. So here we're taking a huge amount of images, and then we're co-adding them. And this is, I think, maybe something many of you have done with ground-based astrophotography. But yeah, so we co-add them all together. Various techniques, there's other names. This is the drizzle. We implemented the drizzle technique, which was developed for the Hubble instrument. The Hubble, I forget exact what instrument this drizzle was developed for, but it basically allows you to increase the signal strength of your images and also increase your spatial resolution. Called subsampling. You're reconstructing the full PSF, and also referred to as a linear reconstruction technique. Especially with lots of these imagers that are taking images of extended bodies, their point spread functions are particularly undersampled, and I can talk more about that maybe later, like getting a little more technical. But doing this reconstruction can be pretty important to getting additional accuracy. But yeah, so basically, initially, this is all we're seeing. We co-add, I think this was maybe 30 images, and boom, now we are able to observe our target. It shows up before, nothing. Now we combine enough images together. There, we can observe Didymos. And so here's just kind of some more examples of, here's kind of what you get by using these linear reconstruction techniques or subsampling co-editing techniques, where these are the original pixel sizes, but by we are able to create super resolution images and get more precise understanding of where the center of that signal is, the center of brightness. Here's it kind of represented as a graph. Again, we're kind of without anything now using the reconstruction. Here's what our measurement residuals look like. So this is basically you're fitting that trajectory line to your data. This is now if you fit everything. Now how far off are all the data points from that best fit? Basically, these are referred to as residuals. So on the bottom, this is in pixel space. So again, early on it's pretty dim. We're getting maybe measurements within 0.2 pixels. Now, towards the end, as it gets really bright and it gets more signal, you see things slowly start to collapse, and by the end, we are getting below 500ths of a pixel, 1 sigma accuracy on these centroids, and how they were fitting. Basically, they were fitting to sub 500ths of a pixel, and then also really this just represents the power of OpNav. We start far away, even though it's 0.2 pixels over here, but in physical, metric space, kilometers, we're just getting so close that the measurements become really powerful. Towards the very end, where you're getting sub-kilometer measurement accuracy, just due to the proximity. You know, you're getting measurements here, but it's really, you're just like, you know, 100 times closer than you were earlier. So you're getting really powerful measurements. Yep.
So you're targeting Didymos because Dimorphos is too small.
Yeah, at this time, you're just seeing the binary system together. You were not able to differentiate the two till the final few hours. So at this time, you know, we were constantly trying to monitor to see if we could observe oscillations in the observations due to the brightness moving around as Dimorphos orbited Didymos. So you're constantly monitoring that, but they were so close together. I think towards the end, we were getting around like a few hundred meter accuracies, a few hundred meter error on our measurements, and Dimorphos' orbit around Didymos is only a couple hundred meters, so it's kind of in the noise. We were never really able to observe it. Here's kind of just some representative images of what things look like on approach. You know, coads. This is I think 30 days out. There's, you know, unfortunately hard to read text here, showing kind of its brightness, trying to keep a fixed stretch just to represent how bright things get. So, you know, here on it's early. It's pretty near the noise. And then it starts to get brighter, starts to get, you know, clearer shaped. It starts to get above the noise, and then you get towards the end where, you know, this was the very last image that was taken and used to perform a knowledge update to understand where we were. And at this point, you know, it's an extremely bright target. Here's another challenge. Again, when you're on the ground and you have your ground-based telescopes, you've got them on mounts. They're sitting on stable surfaces. You know, depending on the precision level of your tracker, you know, you're able to have really precise control. But in space, you don't have that. You know, there's no external forces. So the spacecraft, in this instance as well, is relying on thrusters in this instance to bounce around and to point. So it's trying to say point here and fire these little thrusters back and forth. And so you get lots of motion. And in this instance, there's an issue with the initial GNC attitude system, and it was over the course of 240 images, it was shattering around like crazy. It was just the thrusters were just firing, bang, 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 and you're just absolutely chattering around where your desired target was, which is okay, but you're just moving so fast. We were getting 10 pixel streaks. You know, everything was really streaked out. So that's a really important thing you have to consider in optical navigation, is how stable is your pointing, how well can you control it. So we worked with the GNC team, and they were able to fix that. And so again, before it, we were getting around 0.2 pixels, and then again, we were able to get down to like 0.05 of a pixel by reducing the smear and the noise from all this signature. Oh yeah, here's a fun video here. This is a video I put together of all the OpNav images combined as basically tracking Didymos, and you see the stars, the background stars moving behind it, because we're basically taking pictures every 5 hours, and it's getting brighter and brighter and brighter, slowly brighter, and you're seeing all the stars, and towards the very end, things just start to slow down, you start to get closer, things just start to straighten out, you see the stars are slowing down a little, and it gets really bright, and then that's the last data. So this is that was kind of a collection and alignment of all the optical navigation data, and that was really my 30 days of this mission was generating all of those images, processing them, creating measurements, handing them to the OD team.
What's OD?
Oh, orbit determination. I'll touch on the New Horizons Arrokoth, another interesting different mission. So this was, again, going out to the Kuiper Belt object with a Pluto flyby in 2015. So it's kind of, you're just trying to shoot straight out of the solar system. We get another APL mission. So this is where I really got my start. So now we have very different looking optical navigation images. And this was because, just unfortunately, due to the alignment of the solar system at the time, as the spacecraft was approaching Arrokoth was directly in front of the Milky Way, the center of the Milky Way. And so before with DART, we had very few stars. I mean, you were seeing, we were really having to coad to bring out additional stars. And now it's just all stars. And so, yeah, and there's also the challenge of you're at 43 AU from the sun, so you have limited data. No way you're taking 240 images every 5 hours. And yeah, you have the background stars, and then also, yeah, you're at 43 AU, so you're taking images of this target that has, light decreases, with a ratio of r squared. So at 43 AU, the light is 43 times 43 times dimmer at that distance than when we're at the Earth. So it doesn't, much larger objects are still just much dimmer because the strength of light at those distances is so weak. So we had to, use lots of techniques to leverage this. These, you can see these pixels look really blocky because to save data weight, to save on data, the camera is a 1024 by 1024 camera, but it's just too much data to send down these images. So you bin the pixels on board. So you basically take an image, onboard software says, okay, let's add up all clusters of pixels, basically 4x4 bins. So let's add up a 4x4 array of each pixel and turn it into a 256 by 256. You can get more images, increases the signal, but reduces the accuracy of your measurement. Your resolution is reduced. Yeah.
Is the XY plane, is that pixels or is it something else?
Yeah, these are pixels here. So yeah, it goes out to 256 and 256. And we often just work with 0, 0 being in the top left corner. But yeah, so all these things. So this is really where I got my start at JPL, and especially again with these binned massive pixels, this is where getting to research and implement the linear reconstruction techniques in Drizzle was very important. Because yeah, again, this is the original pixel size, and this is like the same image but with the bin pixels. So you're losing a lot of resolution. So how can we attempt to recover that? So the step here is now, yeah, we've got a crazy background star field. So you really have to look at doing background subtraction. Here's again kind of using subsampling versus not using subsampling. Just the linear reconstruction Drizzle. You get this without it, this with it. Then you do background subtraction. And again, so basically, Arakoth was hiding out right in the corner of this star. I stared at this star pattern every day for multiple months. And because the dynamics are so slow, it just moved very slowly because you're just kind of way out there. And so you could always pull up one of these images and immediately find that little crescent. And it was really fun. But yeah, so we perform background subtraction. Then the target can pop out. And I think I have another video here. So yeah, just much less data here. And everything's moving a much slower. But you're slowly seeing Arakoth get brighter, gets much brighter, and you're seeing it slowly move down. And this is kind of over a similar time period, but just due to the alignment and the dynamics, before you're seeing this thing racing across the sky, and now we're seeing it very slowly shift down and get brighter and brighter. And so that was really a collection of much of the data during that mission. Yeah.
How can you tell what's background?
So what was done was many months before the approach campaign started, the spacecraft took a large data set of images of that exact same region, the same exact settings, and basically that provides us our background. I think technically Arakoth was in the field of view, but since it was so long ago, it was just so dim it would never have affected the images. So that's basically, you get that background data set by taking images again exactly with the same imager, so you're really able to just directly subtract them. But again, you have imperfect pointing, things are bouncing around, the point spread functions are not exactly perfect from perfectly stable, so everything's a little different. You're subtracting things out, but the edges don't quite line up, and you get residual noise poking through because your data sets aren't exactly the same. They were bouncing around in different ways ever so slightly, and so you can never do it quite perfectly. Although better astronomers than I have implemented more advanced techniques who can to really try and estimate these things, and we just never, especially as an intern, did not get around to trying to do that. But yeah, and this is also a nice little go back into the what Chris you brought up earlier on astrometry, because I saw you had that earlier talk. The New Horizons mission was pretty critically enabled by ground-based astrometry. And so that was in the form of stellar occultation data. I think the talk itself was on about collecting stellar occultation data. And so, again, this target's so far out and away, we just really didn't know where it was. But there was an occultation event where it passed in front of a star and teams of astronomers dispersed amongst the Earth, and were able to measure exactly how that star dimmed as the asteroid passed in front of it. And basically this is just ends up just being a really, really powerful measurement to pin down exactly where the asteroid was at that exact time. So it was, in some ways enabled the precision that ended up being executed for this mission was ground-based stellar occultation data. And so you can see this sticker was made before the flyby. This sticker was made years before. And this is based on the stellar occultation data. You're kind of able to get like an outline. And they put together this graphic of what they thought the object would look like based on the stellar occultation data. And when we got the first pictures, I mean, they just completely nailed it. It was absolutely shocking how perfectly they nailed what they thought the object would look like. I'll touch on Psyche real quick. So this is a mission that has not yet executed. It's in flight, a JPL mission to Psyche, a metal world. Largest metal asteroid, 200 kilometers, super high density. Theory is that it is the exposed core of a larger body that was maybe blown apart by some intense event, and so you have this rich iron dense metal core floating through our solar system, and so that's what Psyche's trying to go explore. And so this is an orbiter mission. Here's kind of an outline of its arrival. I think it just did. What did it? There was. I think. Yeah. We're basically it launched in 2023, and yeah, we're basically at this point coming up on its first Mars gravity assist in May of 2026. So it's somewhere right around here. Arrival in 2029. So this is a key mission where, again, before we were talking about point source targets, but now we're talking about images that look like this of fully exposed bodies. And so this is where this technique I kind of touched on earlier, stereophotoclinometry, where you basically, it's the current standard practice for near close body optical navigation. You basically take lots of images of your target and of its surface. You get view angles, illumination conditions. You align all these images, get everything lined up, and then you're basically able to estimate. You have a model for the reflectance of the target, and you're able to estimate slope and albedo, and create basically an albedo and height map of your target body. Doing similar estimation techniques, just doing collecting all this data and minimizing the difference between all your observations and your model. And so you basically are able to just create renders, and then once you have this model of your target and are constantly updating that, you're then taking an image. You take an image. This is what it looks like. Let me render what we think that image should look like. Okay, and now let me just match my rendering to what is observed, and let me triangulate that way, basically, because I have a rendering. I know that this crater is in this coordinate on the body. Okay, I'm able to create that render and match it to the image. Oh, I know exactly where that coordinate on the body is, and so you're able to navigate relative to your extended small body. Autonomous optical navigation. Just got to try and touch on this. Basically, yeah, there are some situations where you just can't execute it from the ground. You have to have round-trip light time. You have decision processes, so you have to do things on board. So that's kind of to maybe track things during flyby, to do an impacting. Impacting can be so precise. You have to hit something to within tens of meters. So you have to you just again, DART last maneuver was a day out. You have to start doing things much later to get those to really get really precise delivery. And so, yeah, you just can't do this whole process. It often takes hours, days. Often minimum time is 24 hours. So we leverage autonomy. So again, Deep Space One, 1998, demonstration of JPL's AutoNav system. So the spacecraft was basically sent in a deep space cruise, and it attempted to do autonomous cruise, where instead of using measurements with the DSN, it actually went around and imaged known planets and known asteroids, and able to triangulate itself that way during cruise. And then as you get close to your body, you just start imaging it and kind of use your eyes to follow your way in, basically. And so, yeah, really ambitious technical mission. And yeah, these are some of the flyby images of some of its executed missions. And yeah, Deep Space One was that really first key demonstration. Since then, again, more implementations of AutoNav. The Stardust mission flew by several small bodies. Then Deep Impact, another AutoNav mission, demonstrated comet impact. So again, here's, basically it was two spacecraft, somewhat similar to DART, except it was a large mothership that would fly by and then it deployed a little impactor. And then there's also APL's SmartNav, which is what DART used for its terminal guidance. There's been autonomous landmark-based optical navigation for sample return. You're heading into the surface of this really crazy rocky body, so we need to use onboard landmark tracking to really precisely go to this exact little area we want to collect our sample. And then, yeah, it's being really pushed in a lot of other missions. It's gonna, as you want to do more and more ambitious, collect more and more ambitious science measurements, get more and more closer to these objects, tighter into closer orbits, you really start to need to leverage autonomy. So it's being brought in and incorporated in a lot of different ways now. And yeah, that wraps things up. I think here's a couple good references for anyone who wants to read more. Here's a great book on the history of deep space navigation and everything. Touches on a lot of what I just said, and some more technical readings. There's a great series by JPLer, Dr. Lincoln Wood, The Evolution of Deep Space Navigation, many papers, and then on optical navigation itself, kind of my mentor, Bill Owen, who kind of was doing optical navigation at JPL for the decades before I got started. But yeah, that's everything.
Awesome. Let's do it. I know this group a little bit, so I suspect we might have some more questions. I think it was great to get some in during the talk, but do you have a few more questions for Declan? Yeah, go on.
Why don't they do everything autonomously? Is it because of the payload, the computation power is not high enough on the
It's really yeah. There are computation challenges for sure, and that has limited things in the past. There's more powerful computers getting pushed into in particular ambitious deep space missions where sometimes the radiation environment is it takes longer for technology to reach these spacecraft, just because of the general level of conservatism with multiple hundreds of millions and billions of dollars of taxpayer money. And then it's also just a risk. It's generally a risk decision of, can this mission just be flown by the ground? Yes, let's just do that, basically. And that's often just what it is. It is in many instances not required, and it would improve on things, but it wouldn't enable things. But nowadays we're starting to really look at situations where it is an enabler, not just an improver. And that's when it really, when it enables something and unlocks these capabilities and is needed, that's when it'll really come into its own. Yeah.
Do you have to compensate for perspective of objects when you're looking from Earth? You see it from a certain perspective, and then once you're in orbit somewhere in deep space, you have a different perspective. Like you mentioned about the Perseus cluster, right? How do you correct for that?
Yeah. So interesting thing if you're doing the star calibrations, like observing the cluster, is really the stars are at such great distances that no matter where you are in the solar system, they look exactly the same. You point in the exact same location because you're just so far away that there is actually no observable difference in where they are. There are some space-based observatories that are so precise that they can kind of measure some of this parallax, some of the effects of your different location. But for some instruments that are used for optical navigation, it's just never observable. You'd have to be outside the solar system. I think New Horizons and the Voyager missions, they're so far away from the Earth's perspective that they would definitely maybe start to be able to see some parallax if they had really precise imagers, and even New Horizons could probably maybe start to do that. But when you're kind of within the solar system, it just all kind of looks the same. You have to be very mindful with asteroids because definitely you're coming at them from different angles from where the Earth has observed them. But for stars, yeah, it's all the same.
So there's got to be some kind of like, in reference to what, right? Like it's all
Yeah.
relative, right? So is it relative to the Earth or the Sun or like?
That's what I was trying to get to with my question, right? I mean, how are you staying true to your trajectory, not just with the DSM, but how's the spacecraft pretty much staying true in three-dimensional space? So relative to what? And
Right.
especially if M15 is about, what, 33,600 or something light years away, how are you making sure that wherever I am right now as a spacecraft, I am within whatever error of trajectory that I need to be in?
So just on the frames and kind of the definitions of things. So often you're estimating everything with respect to the center of the sun, or the solar system barycenter, the gravitational center of the solar system in cruise. So when you get close to a body, it makes more sense to kind of estimate its trajectory just relative to that body. That's kind of what you're observing and what you care about at the end of the day. You're taking science measurements of your body, so it makes more sense to kind of tie things in there. With respect to frames, it's actually, I think, the same frame that all ground-based astronomers know, and that is, it's the ICRF. I forget the exact name. We call it EME 2000, Earth Mean Equatorial, with reference to the J2000 epoch. So it is an inertial coordinate frame defined by, I think, I wish I had this exactly nailed. I think it's the x-axis is the first point of Aries, and then the y-axis is, I'd have to look this up, but it's basically when you talk about something in RA and DEC, that is the same coordinate system that we fly spacecraft in. It's an inertial coordinate system where the XY plane is the equator of the Earth, essentially. And so it is an inertial coordinate system that it's not rotating or anything. It's fixed. The Earth rotates within it, and so we're kind of modeling everything within that. I mean, we have this definition of this coordinate frame, which is tied to inertial points, these stars that just don't move at these great distances. They are fixed. And so you're able to you have your satellite, you have your DSN stations on the Earth. image processing and the orbit determination on board, and maneuver design of doing that all on board. But otherwise, for Psyche, for these examples, for New Horizons, the data is being collected, downlinked through the DSN, handed to the navigation team to be processed, and then passed on to the OD team where they can explore, infinitely more tests and cases to try and estimate the orbit, design a maneuver. Maneuver is designed, and then it is sent back up to the spacecraft, and the spacecraft is told, execute this, and that's the extent. It's basically sending the data, and it's all being on the ground, and then you just tell the spacecraft, perform this sequence of actions to impart the desired delta V.
I said I'd let you go, but I have to ask one last question.
Okay, yes.
Hopefully you guys will enjoy it. So in Star Trek, there's the navigator, which I remember correctly was Chekhov, and then there was the helmsman, which if I remember correctly was Sulu.
Mm-hmm.
Are you both the navigator and the helmsman?
I would say the navigation team, those are two roles within a navigation team, I think.
Okay.
There is, within the navigation team, there's also the other spacecraft team who are actually sending the signals to do X, Y, Z. So maybe there's that other component of there is the spacecraft operations team, who the navigators say, your spacecraft needs to perform this burn. Okay. And the navigator, the spacecraft operations teams are really saying, okay, let's sequence a series of commands telling to actually, we'll turn the wheel and set the dials right and press the button, basically. And so there is a distinction there.
Awesome. Thank
Yep.
you very much. Thanks, everybody.